Let's talk about now one molecule that actually don't have an sp3 carbon with four different substituents, so we don't see a chiral center here. Yet this molecule is chiral. And it's chiral because it lacks a symmetry. So if you see this, notice that because the central carbon is sp hybridized, notice that we have one pi bond here and the other perpendicular. So I'm going to do a drawing of that and say that it has sigma bond here and sigma bond here. But now because I have, say that I have that one here, and here it's showing a pi bond like this, then for the other carbon, I will have this in the center is sp hybridized. I'm just making this bolder line. So this is my pi bond. So the center carbon, we have two p orbitals hybridized, and it's making a double bond to the other side. So another pi bond. This is what I'm showing, right? I hope that you can see that clearly. So here's two bonds. This is a pi bond. And the other is perpendicular, right? And so here I see also that because of that, if this bond is in the plane as it is here, then I have here that the substituents, one is on wedge and one is in dash. So I'm going to draw here hydrogen and chlorine. Notice that I have one green and one white. Now for the other carbon, however, this is, say, that's sp2, and that is sp2. But for the other carbon, since the pi bond is perpendicular to the screen, now we will have in the plane the other substituents. So let's do hydrogen and chlorine, which is what I'm holding here. Let's hold it by the center now. Now, if you think, let's try to see if we have a plane of symmetry. You can imagine having this as bisecting this. Notice that I cannot mirror hydrogen in, say, chlorine, as we did before. This I'm thinking in having something bisecting, so my plane here. Then this do not mirror, right? Even though if I have this plane containing this two, well, I will not be able to mirror those two. Again, I'm doing this operation. Let's drop that one, this, right? This is these, and I don't have that plane of symmetry. But, so this molecule, lacking a plane of symmetry, we say this molecule is then chiral. It has optical activity despite of not having chiral centers, because the doesn't have a plane of symmetry. Now things change if I have a plane of symmetry. So I'm going to do another molecule. Say that I'm making the bonds different now. If you have now this molecule, again, substituted, but now you have, if you put a plane of symmetry, say bisecting this one here in the middle, now you will be mirroring hydrogen and hydrogen. That's a plane of symmetry. It will be bisecting all the way, so it will contain this atom. But if you rotate it, actually, you have another plane of symmetry here. See? You're mirroring this with that. So this molecule is a chiral. These molecules are allenes, and every time you have one of the sp2 carbon with two substituents the same, the molecule is a chiral because you will have a plane of symmetry. But if you have, such as this case, which I had before, say, two different substituents of each of the sp2 carbons, then I no longer have those planes of symmetry, and this molecule is chiral despite of not having chiral centers.